All right, welcome back to PyCSE. Today I want to continue the topic that I started yesterday on statistics and show you a couple of ways I've been thinking about using Python to build statistical intuition and help understand what some ideas in statistics are. So today we'll take a little example, the central limit theorem. And this theorem basically says if you take a lot of samples in the limit of a very large number, the distribution of the average of those samples is going to be normally distributed. And this isn't often part of that statement, but I'll also show you that the standard deviation of that distribution is inversely proportional to the square root of the number of samples that you've taken. So we're going to take a little bit of a path to get there. So let's get started. We'll import NumPy, we'll use that. I'm going to import matplotlib, and we will use the normal distribution for sampling, but this should work for other distributions also. So from scipy.stats, import norm. All right, those are the main libraries that we'll be using. And just to remind you about norm, we can generate samples of norm with our RVS. And we'll just choose a location of 0, that is the average, and a scale of 1. And this will generate random numbers that are drawn from that. And each time we run this, you get a different one. And of course, it will go from plus and minus infinity with the right probabilities. So let's go ahead and make 10,000 or maybe 100,000 of these. So we can add a size argument, and this will now generate 100,000 samples, and I don't really want to look at them, so let's save them here. And let's look at a histogram. We did this yesterday. I'm just kind of reminding you of some things we can do. Density equals true, and let's do bins equals 20. All right, and let me put a semicolon to suppress that output. What you see looks normal. So how can we convince you that it is? So let's make a linspace. Let's go -4 to 4, and then let's plot x comma norm dot pdf of x. And that should put a actual Gaussian curve over this, and you see it's been discretized. Here I use 20. We have so many points, why don't we make it 100 bins? Now you can see like it's quite close to that. So in this 100,000 samples that we have, you can see that it has the shape in the histogram. Let's go ahead and do some statistical analysis. Let's look at samples.mean, and that should be 0, very close to 0, and it's pretty close to 0, and samples.std. Standard deviation, that is also like very close to 1. Now it's not exactly 0 and 1 because we only have 100,000 samples, but it's considered pretty close. Now what happens if we take fewer samples, right? So up here I did 100,000, but let's come down here and ask what happens if we take just 3. So let's go down to here. Let's put this in a variable, and let's use norm.fit so that we can see both properties at once. And what we get now is 3 numbers, and this first is the average, and this is the standard deviation. So this average is not actually that close to 0. And this is close to 1, but maybe coincidentally, now it's a negative average. Now you see 0.7. And if we run this lots and lots of times, we get lots of different numbers. Now the central limit theorem says if we run this a lot of times, like say 100,000 times, and calculate the average of each run, then we should get a normal distribution, and it should have an average near 0. But it doesn't really tell us what the standard deviation would be. So we're going to next look at that. Okay, so let's say, let me get rid of this. Let's generate samples, and instead of a one-dimensional sample, let's say we want 100,000 rows and 3 columns. And let's just look at s.shape here to make sure that's what it is. And so that gives us now a two-dimensional array. And now what I can do is take the average across each row. So let's say mean, let's do s mean is equal to the mean. And if we just do the mean of s, then it's going to give us a single number, which is not what we want. We want to go across the rows, and so I believe we have to say axis equals 1 here. And let's do smean.shape to make sure. That gives us a one-dimensional array now of 100,000 elements. If you put axis equals 0, then it will go down the rows and you'll get a column-wise average. All right, so now we have s.mean. Let's go ahead and look at the histogram of this. And I'll use 100 bins again just for to be nice and smooth. All right, so now what you see is this is what the averages that we get are. It is centered around 0. That's what you might expect. Half of the time it'll be above 0, half the time below 0. Near 0 is the most common one. And you can see here this is about 70%. And that's much higher than the original distribution, right? The original distribution peaks at about 0.4, and this one is much higher. So what does that tell us? Let's go back to norm.fit on s_mean and see what we get. We have an average of near 0, and we have a standard deviation of 0.58. So the standard deviation of the sample mean is lower than the underlying distribution that we sampled from, which was 1. So what happens if we change this to from 3 to 4, right? One of the beauties of Python is we can do that, and it doesn't take us that much more work. What you find out is the mean hardly changes, but the standard deviation goes down. We call this the standard error, by the way. It's the standard error in our estimate of the mean. And as we go to 5, it gets even smaller. Let's do 50. That takes a little bit of time, but you see this number is shrinking, and maybe, I don't know, 500 might be a mistake, but it doesn't take too long. It drops to 0.04. So now, what is that telling us? If we look at this distribution, we have an average of 0 with a standard deviation of 0.04. So we're actually fairly sure about this value compared to when we had only 5 samples, where any single one might be 0 plus or minus 0.4. Okay, so that is basically the illustration of the central limit theorem. Now what we can do is take another step and ask, well, how do we know what this distribution is? Because it turns out that we do. So you might have heard or learned, or if you were in a statistics class, you would learn that this standard deviation is basically this original standard deviation, 1 in this case, divided by the square root of 5. Let's check that out. 1 divided by np dot square root of n, and let's put an n here, and then we'll put an n equals 5. All right, so what we see here is the analytical and the infinite limit result we expect is 0.447. We measure 0.446. That's pretty close. Let's try it out for 3. We get 0.577. We get 0.575. We can make it 30 and 300, and these all go quite close, right? So 0.577, 0.577, and etc. So we can heuristically, or like by inspection, kind of see what happens here. Let's go maybe one step further and make a plot that shows this. So one way we could do that is say for n in 3, 5, let's see, this is going to go as square root of n. So we could choose 9, 16, 20. I'll pick some things that are squares, 25, and 100. All right, and then let's come back up here and copy some of this. We're not going to use it all. So we could say that S is going to be these random samples that depend on N. We will get an average mean there. Let's see. Let's make this all N. We're going to do that because we're going to plot this, and then we'll put here Sn equals this, and then we'll say Sn plus equals S underscore mean dot standard deviation and then let's do analytical N. Analytical N plus equals 1 divided by NP dot square root of N. And last, let's get rid of this, and now let's make some plots. Plot dot plot. Let's see, all N and Sn. We'll make those blue circles. And actually, let's get rid of this analytical N and just have N equals NP dot linspace from 3 to 100. And we'll do a plot dot plot of N 1 divided by NP dot square root of N. All right, now let's run that. So this is going to loop through the values 3, 5, 9, 16, 25, and 100. I think we can get rid of this line. Then it's iterating through those, generating samples, 100,000 samples by this many columns, averaging along each one, and then accumulating the standard deviation of each one of those distributions. Then we have an analytical expression here that we plot, and here's what we see. Each of these blue dots are the standard deviation of those means as a function of the sample size, and the line is the analytical expression 1 over the square root of N. And if the original distribution was something other than 1, we would just replace sigma here, and everything would automatically work out. So this is all assuming that we know the standard deviation of the underlying distribution, and that's a big assumption in this analysis. Like I know it's 1 here because we sampled from that. If you don't know the 1, or if you don't know the standard deviation and you have to estimate it, it turns out you need another distribution. It's not exactly normally distributed, but it follows the student t distribution. And that's a whole other interesting lesson on its own. So today I'm going to stop here and just refresh our memory of what we did. We looked at the central limit theorem, which is the idea that if we take a sample from a distribution, then the mean of those samples will have a normal distribution. And we illustrated that from the normal distribution, where we could see that in the limit of a large number of samples, we see that the means, in fact, become normally distributed, like this. And we showed that the standard deviation of that mean scales as 1 over the square root of n, all by this kind of random simulation, sometimes known as Monte Carlo simulation. But it's a very convenient way of illustrating it. And what this figure shows is if you want to cut the standard deviation in half, you have to double or quadruple the number of data points. So go from 6 to 0.3. We go from this point over here to this one over here. So if you quadruple the number of samples, 1 over the square root of that is half the standard deviation. So you really quickly run into needing a lot of samples to get very good confidence or very good low uncertainty on the mean. All right, thanks for coming to the channel, and if you find this video helpful, please like it, subscribe to the channel, and leave a comment if you want. Thanks, and we'll see you next time.